Hi, this is Ms. Fitzmaurice. This video is an overview of free response number 2. So first I'm going to kind of go through the physical situation, then I'm going to give you the rubric, and you should score yourself and rewrite your answers. So you're not just, giving yourself points, but you're rewriting or you're correcting your answer, then you're reflecting. So in this problem, we have a ball of mass m. It's attached to 2 strings and it's swinging around in a circle. Okay, a bunch of students say some things comparing the 2 tensions, but before we start to think about them, let's take a second and just solve the force buddy diagram problem. Okay, so in this problem, we have this ball. And the ball is at any moment attached to 2 strings. And I'm going to call the diagonal string TD, that's the tension diagonal, and TH, tension horizontal. And then the additional force we have acting is, of course, mg. And I can write out Newton's second law in both the x and y directions. So in the x direction, I have sigma fx equals max. Okay, both TH and TD have x components, so I have TH plus TD, and the way my angle is, so my angle is kind of in here, the horizontal component will be TD sine theta, okay, because sine is opposite, that's this side right here. Okay, and that's equal to max. In this case, my ball's going in a circle, so that's going to be AC. Okay, so I have TH plus TD sine theta equals MAC. I know that AC is V squared over R, but in this case, they tell me about the angular speed, not the velocity, and I know that V is equal to my angular speed, omega, times r. So I'm going to take this and plug it in down here for V. So I have, it's equal to m omega r squared over r. So I have TH plus TD sine theta is equal to m omega squared over r. And I end up with m omega squared and an r on top because I have 1 r squared on top and r on the bottom, and they cancel, so I have TH plus TD sine theta equals m omega squared r. On the other side, I have sigma Fy equals MAY. And so I know there's no acceleration in the y direction, that just goes away. And I have TD, okay, the component of TD that's pointing upwards, so that's this point, and that's going to be TD times cosine theta, because it's our adjacent part, minus mg, and it's equal to 0. So I have TD, I'm going to add mg to both sides, equals mg. I'm going to divide by cosine theta, and so TD is equal to mg over cosine theta. I can take this expression and hang on to it, but I can also use it over here to solve for TH. Okay, so first I'm going to subtract TD sine theta from both sides. So minus TD sine theta minus TD sine theta. And I have TH equals m omega squared r minus TD sine theta. But I know that TD is really mg over cosine theta, so I have TH is equal to m omega squared r mg sine theta, minus mg sine theta over cosine theta. I know that this is really tangent, so I have th is equal to m omega squared r minus mg tan theta. I'm going to take that, I'm going to put a box around it and keep it for a minute. Alright, so now, kind of keeping these two guys in mind, I have to write about the three students and their reasoning. Okay, so student 1 says, I think the tension in the diagonal string will be larger than the tension in the horizontal string, because to support the weight and provide some, it has to both support the weight and provide some centrifugal force. So, what's right about what student 1 said? Alright, so student 1 is correct in several ways. First, since we know that the T diagonal is the only force other than mg, so is the only, having trouble with my styli, so is the only other y force, okay, and must support Fg. Okay, second, TD must have a x component because it's at an angle. However, they're incorrect because it seems like student 1 assumes that both strings take on the same x force. Okay, but using Newton's second law, we know this is not necessarily true. Okay, so in part 3, it says what aspects of student 2's reasoning are correct. Student 2 says, I think the tension in the diagonal string will be larger than the horizontal string. Centrifugal force depends on the radius. Okay, since the diagonal string is longer, radius must be longer and supply more force. Okay, so they are correct that Fc depends on the radius. However, they are confusing radius with string length. Okay, so the radius is really the distance around the point where the ball's rotating, so the radius is really both the same for both strings. Alright, so student 3 says, I think either string could have more tension depending on the values given. And I'm going to take a second and remind us that we solved and we got TH is equal to M omega squared R minus mg tan theta, and we got that TD was equal to mg over cosine theta. So actually that has to be right either tension could be bigger depending on omega and theta. Okay, they're also correct when they say mass doesn't matter. Okay, because in both cases, T is proportional to M, right? There's like an M that I could factor out in both cases. All right. The second claim that student 3 is making is that if omega is large, that we will have a small th, and if theta is small, that we will have a large th. Okay, so they're actually backwards. Okay, so using Newton's second law, we can see that TH increases with omega and decreases with a large theta. Okay, so now in B we have a bunch of equations. Part 1 says which equation best supports student 1's reasoning. Okay, so equation 7 best supports 1's reasoning, since 1 argues that T diagonal is larger because it has 2 components. Okay. One sort of supports student 1's reasoning, since it calculates the ball's weight. Okay. For number 2, it says which equations best support student 2's reasoning. Okay, so student 2 is using the idea that with a different R, you will have a different value for centripetal force. So that's equation 2, since student 2 relates Fc to radius. For part 3, equations 1 and 2 support the argument that mass doesn't matter for each tension. Okay. Additionally, student 3 is using equations 4, 5, and 6 to relate theta to the total force. Finally, in part C, they want us to say which string, if either has the same or has the greatest tension. Okay, and we can basically write this using Newton's second law. We find that TD equals mg over cosine theta, and TH equals m omega squared r minus mg tan theta. So if omega is large, or theta is, okay, and I shouldn't say or, I should say like and or theta is small, TH may be bigger, but if omega is small, TD may be bigger. And I should have said large. Wait, no, that was right. Omega is small, TD may be bigger. Okay, so now to scoring these. Each of the what they said right is 1 point. So for part A, part 1, you have to get both that TD is the only y force and there must be an x component. Okay, and so those two combined gave you 1 point. In part 2 it says assume that both strings take on the same x force, but that's not true. Give yourself 1 point, or if you somehow indicated that the x components didn't have to be the same, give yourself a point. Give yourself a point for pointing out that FC does depend on R. 1 point for pointing out that they're confusing radius with string length, and that R is the same for both. Give yourself 1 point for pointing out both, okay, that either tension could be bigger and that mass doesn't matter. So you needed both of those to get the point. And then finally for part 6 you can point out using Newton's second law that it could be either. In part B, we have 1 point for each, and you need both equations and a good justification. Okay, so 1 point for 7, 1 point for both 7 and 1. In part 2, 1 point for equation 2, Vt squared over R. 1 point for both of these. You could have either 4, 5, or 6. You didn't have to have all 3 of them, but you did have to have 1 or 2, 1 and 2, and point out that it relates to mass. Finally, in part C, there's 1 point for saying that we don't know which one is going to be bigger. Okay, so you can say that however you want, just saying you don't know which one's going to be bigger. There's 1 point for actually solving for each of these, And that's it, 12 points.